Okay, so I'm going to start talking about section 6.4, but before I actually start doing the problems, I'm going to talk just a little bit of theory, and not so much theory that it should bore you to tears, but just enough so you kind of understand why we're studying this next topic. And the big topic, the focus of section 6.4 is logarithms, and logarithms are functions. And they are used to answer when type questions. When something will happen, I'll say when questions. For instance, if I wanted to answer the question, when will the population of the USA be 500 million? That computation would definitely use a logarithm. Or when will 30% of the people in Arizona have a smartphone, if it isn't already? Or when will the 1 millionth person get the flu this year? All these types of questions are when questions, and the computations, the way to solve those questions, would involve this function called logarithm. When we deal with logarithms, they're not hard, but notationally they're kind of messy. So the notation for a logarithm, I'm just going to write a common logarithm down. I would read this as the log, or the logarithm, base 3 of 9. So there's two parts to any logarithm, the base and the argument. In this logarithm, the base is 3, and the argument, I'm not sure if I spelled that right, is 9. That doesn't tell you anything about what this function simplifies to. Every logarithm asks the question, the base to what power is the argument? So the question that needs to be answered, or that's being asked by every logarithm, I'll use the log and logarithm interchangeably, is this: the base to what power equals the argument. So it seems to me like it might be easier just to ask this question rather than to use a logarithm, but symbolically the logarithm is an efficient way to ask this question, and mathematicians use it, so we'll have to use it. So in terms of this problem, the question that's being asked in terms of this problem, the base 3 to what power, I'll make x the what power rather than writing the word what power, is 9. So if you understand the question that's being asked, some logarithms aren't that hard to figure out what they equal to. So this is asking the question 3 to what power is 9. I know that 3 to the second power is 9, so this logarithm is equal to 2. The nice thing about this calculator, this is one of the rare calculators that does logarithms amazingly easily. So I'm going to turn my calculator on. It's in complex mode, that's okay. This button, the log button, that has the, let me just hone in on this a little bit. This log button right here, if I type it, it allows me to enter both the base and the argument. The base is subscripted, and it always puts the argument in the parentheses, and that's a good habit to be in. So this is a log base 3 of 9 done on my calculator, and my calculator knows that it's equal to 2. So that's a real Reader's Digest version of logarithms, but enough to get us started. I'm going to go out of order in this section, and well, let me say a couple more things about logarithms. A couple things that my calculator knows. Logarithms are undefined for 0 and negative numbers. Technically, you get i's with logarithms with negative numbers, but it's really complicated to do logarithms with negative numbers, so for now we'll just say they're undefined. So for instance, if I ask the question, what is the log base 2 of 0? My calculator knows this doesn't have an answer. It's undefined. It's going to tell me some sort of error. The question that's being asked is 2 to what power is 0? If you thought the answer was 0, you'd be wrong, because you'd be saying that 2 to the 0 power is 0, but 2 to the 0 power is 1. So the answer is not 0, because if that 2 to the 0 power is not 0, it's 1. And any number that you might think of to put as an exponent for 2 to what power is 0, it won't work if you tried it on your calculator. When I do a logarithm for 0 on my calculator, regardless of the base, the log base 2 of 0, I get a math error. So this is undefined. And similarly, any negative number, if I gave something like this, log base 5 of negative 10, feels like the answer should be negative 2. This is asking the question, 5 to what power is negative 10? And this side is always positive. If you put a negative exponent in, like if you put a negative 2, and if you thought negative 2 was the answer, you'd be saying 5 to the negative 2 is negative 10, but it isn't. 5 to the negative 2 is 1 over 5 squared, which is 1 over 25. So this is definitely not equal to negative 2, because 5 to the negative 2 power isn't negative 10. Turns out that 5 to any power is always a positive number. That's why this doesn't have a solution. And if I try to do it on my calculator, it also knows. It just knows that logarithms can't be done for negative numbers, nor can they be done for 0. That's not really going to be a huge thing, but it's just something you should know. It will kind of subtly come up in 6-7, and you might not even realize that it comes up there. Alright, now in the section, going in a little awkward order, because I think the middle problems, 19 through 42, are the nicest way to start. So the nice thing about the problems between 19 and 42, although the instructions say do them without a calculator, I'm not committed to that, and if you need your calculator to do them, it's fine. I'm going to do every single problem without my calculator and with my calculator, just so you can start to see how you need to think about logarithms if you don't have a calculator handy. So problem 20 is a logarithm. Every logarithm says the base to what power is the argument. So that's the question that problem 20 is asking. And if I know the answer to that question, then I can I can get the answer without using my calculator. Well, I know the answer to that question is 0, because 2 to the 0 power is 1. I'm not going to write x equal to 0, because there's really no x in the original problem. Just the log base 2 of 1. I could write that if I wanted to. The log base 2 of 1 equals to 0. That would be probably the nicest answer, but 0 is sufficient. On my calculator, if I didn't know that, I type 2 for the base, 1 for the argument, and my calculator would tell me it's 0. 22 is asking the question, the base 3 to what power is the argument 3? And again, I know the answer to that question, so I don't need my calculator, because 3 to the first power is 3. Because 3 to the first power is 3, the answer to this is going to be 1. And again, you have the flexibility of just writing the number that it's equal to, or you could write the problem with the answer as well. So on my calculator, the log base 3 of 3, and you get the 1. Some of these you have to be really clever to do without your calculator. A lot of them, you don't have to be that clever. 26 is asking the question, the base 4 to what power is the argument 4? And the answer is going to be 1 again, because 4 to the first power is equal to 4. So for 26, my answer is going to be 1. And I'll just write the answer without writing the problem next to it. On my calculator, I could do the log base 4 of 4, and I get 1. 28 is asking the question, the base 5 to what power is 1? Because anything to the 0 power is 1, I know the answer is going to be 0. And so I'm able to, because I know exponents really quickly and well, I can get the answers quicker by hand than my calculator. But it's really effortless on my calculator anyway, so it's having the skills of being able to look at the problem and bust out the answer. It's not going to save you a heck of a lot of time. 30 is asking the question, the base 5 to what power is the argument 125? If that's just a common fact for you, then you know the answer is 3. If you don't know your powers of 5 that well, then you don't know that this equals to 3. But the reason my calculator is going to come back and tell me this equals to 3 is because this is asking the question, 5 to what power is 125? And the answer to the question, 5 to what power is 125, is 5 to the third power is 125, so the answer is 3. So again, on my calculator, the log base 5 of 125, and I get 3. So I can blow through these really quickly with my calculator. If you have to go high in math, meaning beyond algebra into the calculus sequence, then you should take the time to get real comfortable with doing these by hand. If college algebra is your last course, or this is your last math course, it's not going to slow you down. You'll notice in problem 32 there's no base written. It feels like the base should be 1 if no base is written, but that's not the case. With logarithms, if no base is written, it's assumed to be 10. My calculator actually has a button to do logarithm base 10 because it's a common base. So if no base is written, the base is assumed to be 10. Which is kind of surprising, because usually if something isn't written, you assume it to be 1. So this problem, the log of 10 without a base, would have the same meaning as a log base 10 of 10, because I can insert a base if no base is written, and that base is 10. The question that this logarithm is asking is the base that's not written but assumed 10 to what power is the argument 10, and because anything to the first power is itself, the answer to this question is going to be 1. And when I go to do this on my calculator, I could do it one of two ways. My calculator has an LOG button without the base, and that LOG button without the base is reserved for base 10 logarithms. So on my calculator to do this, I can do the log of 10 just like that, using just that LOG button. That looks just like the handout, more or less. Tells me it's 1. Or I could use the logarithm button that I'm used to and insert a 10 in the base. Those mean the same. The log base 10 of 10, which is 1, is exactly the same as the log of 10. These are both log base 10 of 10. They're both equal to 1. So if no base is written, you have to assume that it's a 10. You could write the 10 in if you want to, but you don't have to write the 10 in if you're using your calculator, because my calculator has a button that does log base 10 just fine. 34 is asking the question, the base 2 to what power is 32? And again, if you're really good with your exponents, when I wrote that down, you immediately knew the answer, and that's beautiful. If you're not that good with your exponents, then being bound to your calculator is okay for now. So the answer to this is going to be 5, because the question being asked is 2 to what power is 32, and the answer to that question is 5. So again, on my calculator, log base 2 of 32, and you get 5. 36 would be pretty impressive to do without a calculator. It's asking the question, 3 to what power is 243? And I know that 3 to the 5th power is 243, so the answer to this question is going to be 5. But again, I don't need to know too much to be able to do that. So the answer is going to be 5 for this question. And it's not x equal to 5, it's just the number 5. Again, if I wanted to in my answer, I could say the log base 3 of 243 equals to 5. That might be nicer than just writing the number 5, but it's implied. When I answer a question, that's implied that that's equals to the original problem. 38, 40, and 42 are three problems that are, to me, essentially the same. 38 is asking the question, the base 3 to what power is the argument 3 to the 4th? And I know that 3 to the 4th power is equal to 3 to the 4th power. So my answer must be 4. It's not even that much trickier to enter this. So I'm going to do the logarithm base 3 of 3 exponent 4th power, and I get the 4. 40 is asking the question, 7 to what power is 7 to the 8th? And it should be obvious that 7 to the 8th power is 7 to the 8th. So my answer to this is going to be 8. And again, on my calculator, log base 7 of 7 to the 8th power is 8. And 42 is asking the question, the base 2 to what power is 2 to the 9th? And it should be clear that 2 to the 9th is equal to 2 to the 9th. So my answer to this should be 9. So I blew through these kind of quick because either you're going to do them that quickly because you know the exponents that well in your head, or if you don't know the exponent kind of effortlessly, then you're going to use your calculator, and it takes 2 seconds on my calculator anyways. So you should at least try to understand the question that's being asked for every logarithm, because maybe sometimes you'll just know the answer and you won't have to use your calculator, which would be a good thing. Okay, next group of problems give me true statements. They're equations that have logarithms. Like for instance, the problem 10, if I look at the statement, the log base 2 of 8, it equals 3. This is a true statement. I'm supposed to write a true statement in exponential form, which means I have an exponent but not a logarithm. So I need the numbers 2, 8, and 3 with an equal sign and an exponent, and I need a true equation. Real easy to do this. To take a true logarithm equation, this is really 3 equal to 3. And to make it into something without a logarithm, I follow these steps. I scratch out the log, because I'm writing something without a log that's true. I leave the base low. In this case, the base is 2, and I switch the other numbers. So this is considered writing a logarithmic equation in exponential form. So I'm going to cross out the log. The 2's the base. I'm going to keep it the low part. And I need an exponent. I'm going to switch the 3 and the 8. If you scratch it out, it almost looks like 2 to the 8th power. I'm going to switch the role of the 8 and the 3 and get 3 as an exponent and 8 as the number to the right of the equal sign. And I claim that that's another true statement, and let me check to make sure it is. So did I produce another true statement? Is 2 to the 3rd power equal to 8? Because 2 to the 3rd power is equal to 8, I've successfully transformed my true logarithmic equation into an equation that's true with the same numbers without a logarithm. That's called writing an equation in exponential form. If I look at problem 12, that's another true statement. Problem 12 says the log base 2 of 16 equals to 4. And it does. Log base 2 of 16 equals to 4. So this is a true statement. I'm supposed to write a true statement with an exponent that doesn't have a log with the numbers 2, 4, and 16. Easy enough to do. I'm going to leave the 2. I'm going to scratch out the log. The 2 is the base. It's going to stay subscripted. and I'm going to switch the 4 and the 16. The 4 is going to become an exponent. The 16 is going to go to the right of the equal sign. Let me make sure I still have a true statement. So I'm going to go 2 to the 4th power. I said it equals 16, and it does equal 16, so I've successfully rewritten the problem. Problem 14, it's another true statement. The log base 5 of 1 does equal to 0, so this is a true statement. I want to write a true statement with an exponent, an exponential equation, something that doesn't have a log. How do I do that? I scratch out the logarithm. The 5 is the base. It stays low, and I switch the other numbers, 0 and 1. The 0 becomes an exponent. The 1 goes to the right of the equal sign. Let me check out to make sure I've written something that's still true. That 5 to the 0 power is equal to 1. What I wrote is a true statement with the numbers 5, 0, and 1, so I did well. The next two problems, 16 and 18, I can't do as easily because I can't tell you that this is a true statement because I don't know what x is, but I still can go through the procedure. I can take something and write a true statement without a logarithm, even though I won't be able to confirm it as much on my calculator because I don't know how to do this x on my calculator. So I'm going to scratch out the log. The 3 is the base. It's going to stay low. I'm going to switch the 2 and the x. It wouldn't be wrong to say 9 equal to x. Similarly, it wouldn't have been wrong here to say 16 equal to 16 or 1 equal to 1 or 8 equal to 8. Notice, in none of the problems above did I simplify the exponents. If I would have, in this problem I would have written 8 equal to 8. In this problem I would have written 16 equal to 16. In this problem I would have written 1 equal to 1. I could write 9 equal to x. If you did that, there's nothing wrong with that. 18 is a little bit tricky because I don't see the base, and if I want to scratch out the logarithm and leave something low, I need to know what to leave low. Remember, if no base is written, you can write a base in if you choose the base of 10. If no base is written, the base is assumed to be 10. Can't check 18 on my calculator because of the x, but I can do the same thing. I can scratch out the log, leave the 10 low, and switch the 4 and the x, and I get 10 to the 4th equals to x. And if you want to, you can do 10 to the 4th on your calculator. You get 10,000 equals to x. So that's kind of the second group of problems in this section. And basically, most of the problems in this section, the first 42 problems in the section, the only reason they're there is just to get you used to logarithmic notation, really, as much as anything. Now we'll go to the first problems. The first problems give me true statements that don't have logarithms, and I'm supposed to write something with a logarithm that's true. So this is true. Like in problem 2, the statement that's given is 2 cubed equals to 8. And it's certainly true that 2 cubed is 8. I need to write the equation in logarithmic form, which means I need to write something with the numbers 2, 3, and 8, and I need a logarithm. Easy enough to do. To do these problems, to write an equation that has an exponent with a log and still keep it true, I'm going to write the word log. The base of the exponent is going to become the base of the logarithm. So it's just going backwards. And again, I need to switch back the other numbers. So if the instructions say write in logarithmic form, that means I want to see a logarithm, so I'm going to write the word log. Logarithm has a base and an argument. The base of the exponent is going to be the base of the logarithm. And now I'm going to switch the role of the 8 and the 3. I'm going to make the 8 the argument and the 3 freed up to the right of the equal sign. So they just kind of swap roles. Let me make sure I've written a true statement. Easy enough to check. That the log base 2 of 8, does that equal to 3? Because it does equal to 3, I've successfully written the equation in logarithmic form. 4 is another true statement. It gives me 2 to the 5th power equals to 32, and 2 to the 5th power does equal to 32. I want to write a true statement with the numbers 2, 5, 32 in logarithmic form, so let me write the word log because it asks for logarithmic form. The 2's the base. It's going to be the base of the logarithm. I'm going to switch the 5 and the 32. The 32 is going to become the argument. The 5 is going to free up and go right of the equal sign. Let me check this to see if the logarithm base 2 of 32 equals to 5. And it does, so I've done well there. 6 is another true statement. If I did 4 up arrow negative 2 power, I get 1/16. So I have a true statement with the numbers 4, negative 2, and the fraction 1/16. I'm going to write a true statement in logarithmic form. So I'm going to write the word log. The 4 was the base of the exponent. It's going to be the base of the logarithm. And the 1/16 now is going to become the argument. Usually, once the argument is more than just a single integer, I usually put it in a parentheses, but I don't always. But this would probably be the way that I'm going to enter it on my calculator anyways. So I'm going to double check this. My calculator won't let me do it without the parentheses anyways. I wouldn't take points off if you didn't have the parentheses in there. So the log base 4 of 1/16 equals to error. I don't know what I typed. I'll do 1 over x. The log base 4 of 1/16 equals negative 2. Perfect. My statement matches up perfectly. 8 I can't check on my calculator because of the letters, but I certainly can write it in logarithmic form. I'm going to write the word log. The 4 is the base of the exponent. That's going to be the base of the logarithm. I'm going to switch the c and the w. The c is going to become the argument. The w is going to become the what the problem logarithm is equal to. Could not check that on my calculator because I don't know what c and w are. The next few problems are just to get used to my calculator. Used to be that some calculators were way harder to work than this. These are all base 10 problems. Some of these are going to need to be rounded, but most of them aren't. And our calculator does logarithms so easily that this should be a non-issue. So each of these is base 10. I'm going to use the log button without the base because it does base 10 automatically. The logarithm base 10 of 5 is 0.69897. It says to round to 4 decimal places. So I look at the number in the 5th decimal place. It's a 7. Tells me to round that 9 up to a 10. And then I need to carry the 1 over and round that 8 up to a 9. In 4 decimals, this is going to be 0.699. And then if you write the 0 after the 9, it's okay, but you don't have to. I can only show 3 decimals if I want. And because the number in the 4th position is a 0, it's okay not to write it. 46, the log of 1/10 is not going to be so hard for me. Log fraction 1 over 10. Better close the parentheses. And that's actually equal to -1, which means if I was super clever, I can do it without my calculator. Anytime a logarithm comes out to be a non-decimal, I can do it without my calculator. The base is 10. This is asking the question 10 to what power is 1/10? And I know that 10 to the -1 power is 1 over 10 to the 1st, which is 1/10. So I could have done that without my calculator. Similarly, 48 would be something I could do without my calculator, but I have it handy, I might as well use it. So the log of 1 over 100, close out my parentheses, is -2. I think this is the last kind of problem, the graphs. Yes. Three graphs of logarithms to do, and 4 graphs of logarithms to do. Logarithm graphs, I generally put one on the test, and they're a little bit awkward. They're going to be awkward on my calculator, and I'll just do them, and hopefully you get what happens. First, normally, logarithm graphs only they don't exist from all the way from left to right. They kind of have a beginning, kind of a left edge normally. And in general, I can tell you where the graph is and isn't going to exist because I can find the domain of any logarithmic function. To find the domain of any logarithm that has an x in the argument, you solve the equation, or the inequality actually, the argument greater than 0. And this is going to tell me kind of where the graph exists and doesn't exist. In this particular logarithm, the base is 3, the argument is x, the domain is going to be the argument is greater than 0, which means, and I'll show that to you very nicely on my graph, and I'll show you what it means in a second. So I'm going to find 0 on the x-axis, and I'm going to go to that 0, and I'm going to draw a dashed line. The graph is only going to exist to the right of x equal to 0 and won't touch this line. It'll only be to the right of this line. And over here, I'm not going to get any graph. When I start doing my table of values, if I get a graph over here, I've messed up. So generally, anytime I'm asked to graph a logarithmic equation, the first thing I do is I decide where's the graph going to exist. I do that by taking the argument and setting it greater than 0. I'll do this for each problem first. So once I do it for all 4 problems, you'll understand where I'm going with my domain. The nice thing about logarithms is the table doesn't vary. I do the same table for every single logarithm, which is really nice, but also not nice. Because normally 90% of the graphs that I do, I load up some numbers in the x column and I have to fill in the y's. For logarithms, that's the big exception. My starting table for logarithms is the table -2, -1, 0, 1, and 2. Like we did a bunch already this semester, but instead of having those numbers in the x column, they're in the y column, which makes everything harder with logarithms. So now I'm going to fill in the table. How do I fill in the table? I follow my hint. My hint says, scratch out the logarithm, write the equation in exponential form. So I'm going to write this in exponential form. To write an equation with a log without a log, that's exponential form. I cross out the log. The 3 was the base. It's going to stay the low part. I'm going to switch the y and the x. So the function I'm finding points for is x equals 3 to the y. And one at a time, I'm going to use not the table on my calculator because the table doesn't work so well because it doesn't let me put y's in. I'm going to go first, x equals 3 to the -2. Not so hard on my calculator. 3 up arrow -2 is 1/9, and I'm going to put that in the x column. So the first point I'm going to graph is 1/9 comma -2. And then I'm going to put x equal 3 to the -1 by putting -1 in for y. So I'll go 3 exponent -1, and 3 to the -1 is 1/3. So the second point I'm going to graph is the point 1/3 -1. And then I'm going to plug 0 in for y. I'm going to get x equals 3 to the 0. Anything to the 0 power is 1, so 3 up arrow 0 is 1. And then I'm going to do x equals 3 to the 1. 3 to the 1 is 3. And then x equals 3 squared, and 3 squared is 9. So that's my table of values. When I plot those points, they're going to fit so nicely with that dashed line that's going to be impressive. So in general, first thing I do when I'm asked to graph a logarithm is I find out where there isn't going to be graphed by taking the argument and setting it greater than 0. Then I scratch out the logarithm, leave the base low, and switch. That gets the problem in a form that I can use my calculator to generate x's. Every logarithm that I graph, I use the same table. The unfortunate thing is the starting numbers are in the y column as opposed to the x column. And then I take each one of the numbers and plug them in for x. And now I'm going to plot my points the best I can. So I'm going to plot the point So on the y-axis, I need to go up to positive 2, down to negative 2. Now on my x-axis, I need to get all the way out to 9. Should have made graph paper on these, but I didn't, and you probably don't have it in front of you anyway, so you can do exactly this. Now I'm going to plot the points the best I can. The point 1/9, negative 2, 1/9 is about there. It's just really close to the origin in terms of 1/9 on the x-axis, and then down 2. So that point right there, that's the point 1/9, negative 2. It's just to the right of the y-axis. It's 1/9 of the way between 0 and 1, and it's down 2. The next point, 1/3, negative 1, it's about 1/3 of the way between 0 and 1 on the x-axis and down 1. So it's not all the way. It's not even halfway over to 1. And then the other points are easy. 1, 0 is on the x-axis. 3, 1, I go right 3 and up 1. 9, 2, I go right 9 and up 2. And I'm going to connect the points. Off to the right, the graph very slowly goes up forever. It never stops going down. It goes up forever off to the right. And then around this dashed line, it's going to go down forever. Eventually, it's going to go down to y equals negative infinity. But it will always be microscopically to the right of that dashed line that I made, the domain kind of boundary. First logarithm graph is probably, you might feel completely lost, and that's completely fine. After I do the next couple, you'll start to get in the groove, because they're just not that hard. I'm going to use my calculator to get all the x's. They're lovely, they're really, really, really systematic in some sense. So they get to be nice. So I cruded this paper up, so I'm going to do this whole graph of 52 on another sheet of paper, and heck, I might as well do one where I have graph. So I'm going to graph y equals the log base 3 of x minus 2. So I'm going to attempt to graph y equals the log base 3 of x minus 2. For any logarithm I'm going to graph, the very first thing I do is deal with the domain, because that's going to tell me where the graph exists and where the graph doesn't exist. I take the argument, which is the part that's not the base of the logarithm, and set it greater than 0. For this, I'll add 2 to both sides. The domain of my graph, or the domain of this function, is going to be x is greater than 2. And on my graph, I'm going to find 2 on the x-axis and draw a dashed vertical line through it. Because the domain is x is greater than 2, the graph will only exist to the right of this line, and any place to the left of that line, there won't be any graph, because the domain is only to the right of 2. Anything to the left of 2 is less than 2, and that's out of the boundary region for my domain. So immediately I know the graph is only going to exist to the right of that dashed line. Now I'm going to scratch out the log. I'm going to leave the 3 low, and I'm going to switch the other pieces. I'm writing in exponential form. So in exponential form, it's going to be 3 to the y power, and then I can free the x minus 2 from its parentheses. For calculator purposes, it's going to help a bunch if I solve this for x. So I'm going to add 2 to both sides. And on the left side, I get x. On the right side, I get 2 plus 3 to the y. You can't add those and get a 5. You can't add something with an exponent to something without an exponent. Now I'm ready to do my table. So I know there's no graph to the left of 2 because the domain, you take the argument and set it's greater than 0. Before I go to make my table, I get an exponential form of the logarithm. I cross out the logarithm. When I cross out the logarithm, the base stays low, the 3 stays low. I switch the y and the x minus 2. The x minus 2 doesn't need to be in parentheses when it's freed from the log. Added 2 to both sides. Every single logarithm that I do, I use exactly the same table. I use -2, -1, 0, 1, and 2, but unfortunately in the y column. Now I'm going to find each x by using this formula right here. I'm going to go x equals 2 plus 3 to the negative 2 for my first point. And let me just do that on my calculator. So 2 plus 3 up arrow negative 2. And I get 19/9. I can't graph 19/9. Let me make it into a decimal. 2.11 repeating. So the first point I'm going to graph is 2.11 repeating negative 2. And on my graph, 2.11 is just to the right of 2 and then down negative 2. So that point's about right there. So it's just to the right of 2, 2.11, and down negative 2. For the second point, I'm going to take negative 1 and plug it into that y. I'll get x equals 2 plus 3 to the negative 1. Use my calculator again. 2 plus 3 up arrow negative 1. Another fraction, I don't like that. Hit the SD button. I get 2.333. So 2.33 repeating. So I go 2.33 on the x-axis, which is not quite halfway between 2 and 3, and down 1. Because that's the point x equals 2.33, y equals negative 1. So I go right to 2.33 and down 1. Third point, I go x equals 2 plus 3 to the 0, just changing that y to 0. That one I could do easily without my calculator, but I got my calculator here. I'm going to use it. That gives me 3. So now I'm going to plot the point 3, 0. And then I'll go x equals 2 plus 3 to the 1. And get the point 5, 1. And then lastly, x equals 2 plus 3 to the second power. And I get 11, which is off my grid, but I think I can fudge it. So 10, 11, and then 2. So I made my table of values, and just like the last problem, off to the right, the graph just kind of slowly works its way up. It goes up slowly forever to the right, and once we get to that dashed vertical line, it shoots all the way down to negative infinity, and it never crosses nor touches that line. It always is microscopically to the right of that line. Again, this was question 52 for what that's worth. Much easier for me to graph on graph paper, but you don't need graph paper to do these graphs. 54 wants me to graph y equals the log base 3 of x plus 1. So again, I'll pull out some graph paper just as easier for me. So 54, y equals the log base 3 of x plus 1. All logarithm graphs, the first thing I do is find the domain. And that's going to tell me where the graph exists and doesn't exist. For the domain of the logarithm graph, you take the argument, set it greater than 0. For this one, I'm going to minus 1 from both sides and get the domain as x is greater than negative 1. And then pictorially, I'm going to find negative 1 on the x-axis and draw a dashed vertical line through it. The graph is only going to exist to the right of that because it's greater than. If it was less than, the graph would only exist to the left of that. So anywhere to the left of that dashed line, there isn't going to be any graph. Now I'm going to work on my table of values. I'm going to get the problem written without the logarithm. To get this problem written without the logarithm, I need to scratch out the logarithm. That causes me to leave the 3 low, and I'm going to switch the y with the x plus 1. When I do that switching, I don't need the parentheses anymore. So step 1, I found my domain. My domain is just taking the argument greater than 0. Step 2, write something without a logarithm. You scratch out the logarithm, the base stays low, and you do some switching. I'm going to solve this for x because it makes it easier for me. So I'm going to minus 1 from both sides. And I'm going to write this like this. It's easier on my calculator to enter it like this. And now I'm ready for my table of values. Every logarithm, I do exactly the same starting table. And very specifically, I put the numbers negative 2, negative 1, 0, 1, and 2 in the y column, and then I go to find the x's. My first x is going to be x equals negative 1 plus 3 to the negative 2. Break that out of my calculator because I don't want to do those ugly decimals or negative exponents by hand. So I'm going to go negative 1 plus 3 up arrow negative 2 gives me a fraction. I make it into a decimal. It's negative 0.8 repeating. So it's negative 0.888 repeating. And on my graph, negative 0.8 is to the left of the x-axis and almost all the way to negative 1, but it's still bigger than negative 1, so it's slightly to the right of negative 1, then I go down 2. So my first point is about right there, just off that dashed line. My first point is generally always just off that dashed line. My second point is going to be a little bit further off it, but still pretty close. So I'm going to go x equals negative 1 plus 3 to the negative 1. So I go negative 1 plus 3 up arrow negative 1. Don't want that. Well, negative 2/3 I could actually graph. But if I wanted to, I can make it into negative 0.6 repeating. But negative 2/3 that I actually can comprehend. Or negative 0.6 repeating. That is slightly more than half the way between 0 and negative 1 and down 1. So I'm going to call that about there. So it's definitely, I have the down 1 part, and then it's debatable if that's negative 2/3 or not, but it's close enough. Third point, x equals negative 1 plus 3 to the 0 power. And negative 1 plus 3 to the 0 power is apparently 0, because that's negative 1 plus 1. So I'm going to go through the point 0, 0. And then x equals negative 1 plus 3 to the first power, and x equals negative 1 plus 3 to the second power. So negative 1 plus 3 to the first power is going to be the 0.21. That's easy to plot. And then negative 1 plus 3 to the second power is going to be 8.2, and also not that hard for me to plot. All my graphs that have bases that are integers, they start to look the same. So my graph is always going to stay slightly to the right of this dashed line, and it's going to go through all the points. Off to the right, it's going to shoot up real high, and it'll never cross nor touch this dotted line, but it's going to go all the way down to negative infinity. 56 is the tricky one because the base is a fraction. That kind of flips the graph over, but it's not going to be so hard because we have a lovely calculator. So if I'm doing 56, which I would never put on the test because it's trickier, 56, y equals the log base 1/3 of x. First thing I do is find the domain. For the domain, I take the argument x, set it greater than 0. There's no algebra to do there. That is the domain. So this graph, I find 0 on the x-axis, draw a dashed line through it. Greater than that is to the right. So over here, there's going to be no graph. Step 1, domain done, vertical line dashed. The graph is going to exist right to the right of that line, but not to the left of that line. Now I'm going to scratch out the log and switch. So I have y equals the log base 1/3 of x. Scratch out the log. I get 1/3 to the y power equals x. Probably should put that 1/3 in a parentheses. It's going to help on my calculator. I think if I didn't put it in a parentheses, it might get confused. And now my table of values. Easy, easy, easy because my calculator. Every logarithm I use exactly the same starting graph. First point, I'm going to go 1/3 to the negative 2 power, and I best do it in a parentheses. So parentheses fraction 1/3 parentheses exponent negative 2, and I get the point 9 negative 2. So 9 negative 2 is down here. And then I do 1/3 to the negative 1 power. I could just use my back arrow, delete the negative 2, change it to a negative 1. Yeah. And I get 3 negative 1. So that point's about there. And then I'll do 1/3 to the 0 power, and I know that that's equal to 1, but I could just backwards delete, delete. 1/3 to the 0 power is 1, because anything to the 0 power is 1. So I get the point 1, 0. And then 1/3 to the first power and 1/3 to the second power. Anything to the first power is itself, so when I do 1/3 to the first power, I get 1/3. 1/3 positive 1. 1/3 is about half the way, a little bit less than half the way between 0 and 1, and then up 1. And then the last one, 1/3 squared. Back up, change the 1 to a 2. I get 1/9. And then 1/9, again, it's just off that dashed line and up 2. So when the base is a fraction, it flips the graph over. The graph still is going to stay just to the right of the dashed line that I drew for the domain, but it gets flipped over, meaning it goes up to positive infinity and kind of goes down forever as it goes to the right. The fraction logarithm graph, I can't say. The fraction base, I don't think I've ever put on a test, so it's not really that crucial. But the other few problems, the problem 54, where first I find the domain, then I scratch out the logarithm, switch the y and the x plus 1, use my starting table, that's definitely test worthy. As is this problem 52, the log base 3 of x plus 2. That's the kinds of questions I consistently ask when I do this, when I do the test over graphing logarithms. So that's the whole section. We're getting close to the end, so just don't fade on me, because if you fade on me, bad things will happen, and your grade will go down, and you don't want that to happen for this test, especially if you're going on to Math 151, because this chapter we almost duplicate in Math 151.